Although I don't know why he said that. I need to see I need to look at it more closely.
So yeah, I'm right now looking at like his week 3's third video, and he's doing the one on Jay's attendance, and he's sampling with replace equals true for that one.
This is lecture 3 now, because I don't know. I probably can.
Yeah, it was.
I don't have the YouTube, but I can look at the lectures itself.
It was 3C.
Okay. Is this the sign test?
No, bootstraps for t-tests in lecture 3C.
Okay. No, do you mind sending the video in the chat? Because I don't think I can access yet. And I've never actually watched the lectures. I probably need to. I also probably need to see the context if I explain it. Okay, let's see. Okay. Do you know where it is?
At 10:06 is the first time he's using.
Okay, let me see. Okay.
Yeah, and then the next time the next 3 times he does it, he always has replace equals true.
Yeah, let me see for a second. Okay. So I think that the issue with when your replace equals true, right? You may actually end up with repeat samples, repeat things in your sample. So the issue is that it would depend basically, right? So I think the issue to me when your replace equals true is that it depends on what it could do things to your data basically, right? So I have to look at the question more carefully, but replace equals true because it's possible to get the same value twice. You should think about whether or not that makes sense for your data itself, basically, right? So if it's the case, it doesn't make sense to have duplicates in your data. When you put replace equals true, you may actually get them, and that could be why he docked off marks in your assignment for a logical conclusion mistake, in the sense that it's entirely possible you ended up with duplicates that you shouldn't have had, basically.
Okay, because the only thing is in his examples, his data has duplicates, and he's his data. I'm pretty sure has duplicates, and he's using replace equals true.
But in the assignment, so I didn't need to look a bit careful because in the solution it doesn't appear like there's duplicates, and that's why you put sample equals b, means that it hasn't. Or let me see it in his actual assignment. I don't think he has duplicates, and I don't think he. Yeah, so it looks like in his assignment he hasn't done that basically, right? So it looks like he doesn't really want to have duplicates in his assignment, so he doesn't put replace equals true because the default is false basically. But I need to do some extra work to see. But I think that the thing is that it depends. The short answer is it depends basically on the actual DTB data structure. It could be the case that in Ken's solution, in fact, you shouldn't have had duplicates in your data. It doesn't look like they're supposed to be. And that's probably why, could be why Bo docked you. But you probably need to speak to Bo or Ken about that to know exactly why you lost marks. That's my guess. Basically, it depends on whether or not you're supposed to have duplicates.
Yeah, it makes sense. It's just all the times I've learned about bootstrapped in this class and other classes, we've always used replace. So
yeah, and I understand because when you replace, you get a binomial distribution.
Yeah,
when you don't,
you could have
basically, right? So I would take that up with Ken or ask Ken just for feedback, because that's probably something you might want, because to my knowledge, when you put replace equals full, well, it's not that I know it's true. When you put replace equals
Yeah.
true, you get a binomial thing. You put replace equals false, you don't, then it becomes, it's a different discrete distribution, right? So
Yeah, and this
and
for
it's
this
no
type of
longer
test,
independent
maybe it's
trials,
better
right?
to use.
Yeah, so it no longer becomes independent trials. But yeah, that's a question you want to take up just for clarity's sake, and also to make sure that you understand why. Because I personally, I'm not entirely sure why Bodoc marks. So I suspect it's because they did this new data, but I don't know without having doing this on myself.
Yeah, it wasn't even really, I don't think it's the main reason I was losing marks anyways. I didn't do terrible because of it anyways, but I was just wondering because we'd always use replace equals true, but thank you.
So can you record, Christina?
Oh yeah, it's already recording.
Okay, so I just want to point out that there was some upset about the assignment in the previous tutorial, and I guess I just want to kind of point out that I'll quickly go to Ken's notes quickly so that we kind of can see what constitutes the grading scheme. So you're not actually being graded based on each particular question. You usually in a normal setting, there'd be question 1 worth 2 marks, question 2 worth better. But notice that there's no such thing in this assignment because you're being graded on a gradient, right? So it's not that you're being graded based on each individual question, you're being graded holistically, which means that if you make a lot of mistakes, you will be at 6 out of 10 or lower, basically. Right? So this means that you have a big coding mistake, or you logically misinterpreted a question in a very obvious way, right? This may be when you have small errors, you get, but everything else is for the most part correct, you get 7 out of 10. To receive 8 to 10, you should have really, honestly, no obvious mistakes, basically, right? 8 out of 10 means that like your work is pretty good. You didn't have any obvious coding errors. Your solutions may not be perfect, but they're for the most part accurate. So for instance, if you're asked, is the distribution skewed, and you say it's right skewed, but you don't provide any kind of context of what it means to be right skewed, you may get 8 out of 10. Almost no one gets 10 because you have to show some insights beyond the scope of what you were asking your assignment based, which means that, like, for instance, and I'll kind of elucidate what that means in the framework of, like, because some people might want to know. I'll elucidate what that means in the framework of, like, this assignment, or in the framework of, like, the example we go through in class, right? What it means to be exceptional. It's kind of rare. You have to provide some extra insights that you may not have been asked to do within the assignment itself. But if you did a really good job in the sense that, like, you had no coding errors, your insights were very on point, you had great grammatical structure, it was very clear to the grader, you'll get 9 out of 10. But rare means you reinvented something. You kind of said something really insightful. You weren't asked to do it, but you did it anyways. And then we as a graders kind of knew what 10 out of 10 was, right? So I've seen it happen. I've given 10s, right? But it's kind of rare. So if you did an excellent job, you probably get 9 out of 10 unless you did something really exceptional. So you can see it's on a gradient. It's not like, it's almost like you have to complete the assignment and then you have to kind of complete it well. It's not like you're being graded on each individual, it's the whole of the assignment more so than the parts, right? So I'll just kind of leave that there because there were some upsets last tutorial about this, and I totally understand because these are your marks, right? But if you want to do, these, sometimes it's better to be, in some sense, penalized early, so you kind of look at where you went wrong and then try not to do that next time. Whereas if you kind of get high marks earlier on, you may not know where you made a mistake, and then you may make it again, basically, right? So I think that that's probably something to kind of keep in mind, right? Don't be discouraged because he does drop the lowest 2 assignments, so it's not the end of the world if he didn't do as perfectly as you would have hoped, basically. Yeah, so now this class we're talking about the new test, Geoq plots, and the matched pairs. Now, you might ask yourself, why do we care about the Geoq plot? I mean, didn't you already teach us the histograms and the box plots? Yes, but not quite, right? Because sometimes your box plots and your histograms fail. In what sense? Well, if you look at the last assignment, assignment 2, you were asked to draw a histogram for the cholesterol level. This is assignment 2 that I graded. And it didn't look nice when you just looked at it without actually, manipulating the bins in some sense, right? And this is because sometimes you don't have enough data in your bins to get a clear shape of the distribution. When you have a small sample size, it doesn't always look obvious what the distribution shape is. This is why sometimes your plots may fail you. So even somebody asked me, how do we know what bins to use? And I said, they can give you a formula, right? You can kind of check to see. And it's a function of your, and it's in the solutions assignment too. It's actually a function of your sample size. When your sample size is small, you can imagine there may be some bins where you don't have any data, right? So if you look at here, for instance, there are some bins where there's no data, like for here, for instance, right? So you may want to choose a bigger bin. So you can smooth over the bin. You can smooth, it's like a smoothing process. It smooths you over your bins. So you don't have these gaps basically. When you choose a bin that's too big, when you have a data set that's too small, you lose the structure of your data basically. But sometimes even that can fail too. You seriously get no insight, even if you make your bin small. So what do you do next? Sometimes in this framework, the QQ plot gives you more, right? So I'm going to go back to our trusty empty cars example. And I'm going to give you two ways to plot this in R. I don't use this one, but I feel like with base R, it's probably the first place we should start, right? So this is the histogram for weight, right? So you can see that we looked kind of somewhat uniform to me, right? It doesn't look that skewed. It looks uniform. And uniform distribution, as you guys know, the uniform distribution is actually symmetric, but it doesn't have a clear mode, right? So you can imagine that because it's kind of symmetric in the sense that like every frequency is the same, but it doesn't have a clear mode, you could ask yourself, what should the histogram, what should the QQ plot look like for such a thing, right? So this is the function in base R. You can see that this part's not really too important. It's just me filling with the prettiness of the actual plot, but what really matters is this part here. The qqnorm, you give it a weight, you give it the variable, which is weight. And then when you want to put a line through it, you use QQ line. If I don't use QQ, if I just run this by itself, it will do the following, which isn't good enough because I cannot tell what is going on until I draw the line too. So let me put the line in, which is the next part. It looks like this. Now, maybe I should elucidate to you guys what the theoretical quantiles are. This theoretical quantile along the x-axis constitutes the standard normal distribution, right? So you know the standard normal, it has mass between -3 to 3. And really the mass tapers off if you go too far into the extremes, right? So it's centered around 0. Now, the extent to which your actual sample tracks this theoretical quantile is on the line. If your data truly is normal, then there should be a one-to-one map between your quantiles of the standard normal and your sample quantiles. The extent to which this doesn't happen would kind of elucidate to you guys, right? The extent to which you have a skew in your data, right? So this is things to keep in mind. And I'm going to pause as to what this shape is. I'm going to give you I'm going to give you 3 different shapes for you to know, for instance, when is a QQ plot looking normal? When is it looking right skewed? When is it looking T distribution, T distributed T, right? So now let's actually look at, so does it look symmetric to you? Let's hold this on basically. Let's look at normal data. So I'm going to sample something I know is normal, right? So this is a normal distribution with sample size of 30, 2. Mean is 2 and the variance is 1. So now I'm going to do a transformation to a table because notice that you cannot actually feed a vector into the QQ plot. You had to feed a vector. You had to feed a data frame. This is why I had to convert it to a table first so that it actually kind of works, right? So I converted it into a table, and if I just run this part here, for instance, right? What do I get? I get a coordinate system with nothing on it because I haven't actually told the function to do anything. So I'm going to put the QQ, I'm going to put the QQ, this gives me the point itself. If I do this, I get what? I get just the point itself with no line. So you can see that it does the same thing as if you just put this up to here in base R. You have to ask for the line, which is what you see here. So when I keep adding features to my plot, I get the entire QQ plot, which looks like, oops. Looks like this. I meant to do this one first. So this is normal data, right? Now, how do I know it's normal? For the most part, the points actually track the line, right? So I don't see any kind of obvious erroneous failure to track the line. If in fact, if I make this sample size even bigger, let's suppose I made it 100, what happens? It looks even more obvious, basically, especially in the middle. If I make it 1,000, it will truly track the line, basically. That's how you know it's, if you increase your sample size, it really actually tracks the line almost perfectly because it truly is normal data, right? So now this is what you expect to see. When your sample data is actually normal, it will track the theoretical quantiles because there's a one-to-one map between, you can always find a one-to-one map between any normal distribution and a standard normal, because you know that a standard normal is a translation of any normal by its mean. So you guys all took 57, you know that like a standard normal is a translation of any normal distribution from its mean, and then it's standardized by sigma, basically. So this is always, there's always a one-to-one map between any normal distributions, right? But the extent to which you don't track the line will kind of elucidate to you, you don't have normal data. You guys know the gamma is actually skewed, right? So let's actually sample from a gamma distribution. It is 32. You might say, why are you choosing 32 all the time? It's because the data frame for MT cars has 32 observations. I wanted to compare the initial weight class to different distributions that I know have a particular structural form, right? So let's see. So the reason why I have this, by the way, is because if you don't, the table is, this is a data frame basically. So this is a data frame. If I put it into my console, you see that it does this. It's a data frame now, basically, right? It's a 32 by 1 table. It's a data frame. If I try to do a histogram of y, it will not run because you cannot put a data frame inside of an actual function. This is why I have y $y, because it doesn't. You cannot do this. It will tell you x must be numeric, but this is a data frame. So what I'm actually doing here is I'm pulling the vector y from the tibble y, basically. So this is why it's y $y. This is data frame y here, and I'm pulling the vector y. So when I run this, it actually works. That's why it looks like y $y. You might think, what the heck is like y $y? But y is the actual tibble, and I'm pulling the vector. That's why it looks like that. It looks ridiculous, obviously. But you can see that this is actually completely skewed to the right. Look, notice the mode is centered between 0 to 1, and it's really skewed to the right of this, where this is clearly classic right skewed data. So you can expect that when I look at the QQ line, it should not look like what you see up here. And by the way, when you want to justify your answers, to kind of make it clear what constitutes at least 9 out of 10. If you're asked to make a plot, you should justify why you chose a QQ plot, right? So maybe you were asked to determine if your thing is actually a normal, and you said, I looked at the histogram and it wasn't clear, so I drew a QQ plot to determine if the points tracked the line, basically. That's one logical step you might want to take to justify why you're using the QQ plot. You might want to say something like, well, notice that this is actually normal because there's a one-to-one correspondence between the theoretical line and the sample, because the data trends the actual line. That's a full conclusion. Don't just say from the QQ plot it looks normal, because what does it mean to look normal, basically? You haven't really said anything, right? And similarly, if you look at your data and it looks skewed, like it's going to look here, you can see that, if I run this, it looks like this, which is very skewed, right? It looks like an upward U. Now you cannot just say, look at the points. It is not trending the line, therefore it is right skewed. You have to say the points show an upward cusp. You can see that the points, it shows an upward cusp. This is why it's right skewed. The points do not trend the line, basically. This is a complete comprehensive solution as to why your data looks right skewed. Not just say, look at the QQ plot. It looks right skewed, and move on, because what does it mean to look right skewed? You haven't elucidated what your plot looks like. So these are things that people lost marks for in the last couple of assignments, because they would say the data looks right skewed, but they didn't really elucidate what it means to look right skewed. So we as the graders had to be convinced, basically, that you were like fully elucidating your answer. So that's why we kind of had a peek there. All right, so this is why we had to peek to see if you were really fleshing out your answers. Yeah, so you can imagine that left skew data that would have a downward cusp. Instead of looking like this, like an upward U, it would look like that, like a downward U. And you could then say it's left skewed because the cusp is looking downwards. You know, the data is not turning a line, basically. The other one you kind of would see a lot is T distribution, right? So the T distribution also has a very distinct look because it almost looks symmetric in the way the normal distribution does, except you guys know that it has long tails. So it almost should look normal in the center. You should trend the line in the center, but then when you look at the fade off into the sunset, literally it fades into the sunset in the tails, it doesn't trend the line of the tails because it's long at the tails. Instead of actually putting no mass, so you guys know the normal distribution cuts off after like -3, but in fact the T distribution will keep going basically because it puts mass on outliers in a way that T distribution, in a way that the normal distribution does not. Right, so let's see what happens if I just take, for instance, a random variable that is distributed T with 32 observations, and then degrees of freedom is n-1, so this is why it's 32. So just to kind of show you guys that if I do RT, this is random variable of something that is distributed T, you can see that you put n and the degrees of freedom. So this is why I'm doing like n is 32, then n-1 is 31. Right, so now if I run this and make a tibble, and actually, even if I just look at the histogram just for fun, so W $W is me pulling out the vector W from the tibble W, it will look like the following. You can see that it still looks horrible, obviously, because the sample size is too small. This is actually an example of why a histogram doesn't really work here, right? So you can see this is a perfect example when you ask to write a histogram and stuff, or give a display as what your data looks like. So if they say, make a display, you know, like determine if your data is normal, and you make a histogram, you would see that it doesn't really give you much insight. So this is one example as to why you might say, okay, I should look at the Geoq plot. You know, when I first looked at the histogram, it didn't look very good. Basically, I didn't get some extra information, right? Because sometimes you can freestyle it, right? So sometimes I always put like, why did you choose this particular particular plot? Because you can choose other plots, and sometimes I may have chosen other plots myself, but you have to justify why you chose them. So if you're asked to draw like a plot, and maybe you wouldn't want to choose a histogram because it doesn't look very good here. It might be that you choose a Geoq plot because of this ugly histogram that doesn't give you any insight. All right, so if you run this, you can see it looks better than what you saw here. So you can see this is clearly not symmetric. If you look here, it doesn't do a bad job, except when you get to the tails here, right? Where you can see that it's T because you have these long tails and it moves really far from the line when you get to the extremes. Now, what happens if I increase my sample size, right? So if I increase the sample size to, 199, because degrees of freedom is n-1, I run this and I get something that looks even more distributed T. You can see that you still have this tracking in the center, but the tails don't look right. Right, so if I increase it to 1,000 again, you can even see it. You can see that still the histogram is doing better because you can see now that you can see the long tails coming in, but it's still not great. Let's move it to 1,000 now. Let's see what happens to everything basically. So you can see that it really is starting to look. Actually, you want to see what's kind of interesting here? What happened here? This is not T, right? This is no longer. I claim it's no longer looking quite T. You can still see some kind of outliers here. But it's starting to look more and more symmetric, right? That's really the center limit theorem there, ironically, because it's really saying when your sample size is large, things start to look more and more symmetric, right? So ironically, like you would think it would look T, what it does is it looks more and more like symmetric, right? Or more normal or Gaussian. Okay, so anyways, you can see that when you make it to 1,000, it really looks actually quite Gaussian. This is the central limit theorem here, right? So you see that it tells you for large sample sizes, things look more and more Gaussian, like normal, right? This is what is actually happening here. So this is kind of funny, right? At some point, distribution starts to, when degrees of freedom are very large, right? So let's make a note here. For large degrees of freedom starts to look Gaussian normal, right? So it starts to, obviously, that's the central limit theorem there. But yeah, so you can play around with things and see what happens. I'm gonna put this back. Yeah, so it's kind of cool how statistics, obviously you can simulate the statistics in action, but it's also cool how the QQ plot changes as a function of what your data is actually looking like, right? So I kind of give you guys the ability to play with the stuff yourself. You like change the actual sample size and see what happens to your QQ plot. And actually, if we go back to the question here, then we can actually answer whether or not we think this looks actually normal. It's not right skewed completely. This is why I'm further convinced that this is not quite right skewed, because to me, this doesn't look like this completely, but it's not normal either. It looks like something uniform, something slightly symmetric, but not quite normal. So it looks somewhat symmetric because the uniform is somewhat symmetric, but it doesn't look quite normal. This is why I said, let's look at the three big, different distributions where we actually just make a conclusion, because it doesn't look that right skewed to me at first glance, ironically. Yeah. Any questions about this? So make sure when you guys kind of put your answers together, you're very, very detailed as to, like why you think certain things look the way they do, right? Cool. Now, when is this going to help you? It might actually help you when you look at the matched pairs, because especially when you have small sample sizes. So this QQ plot might actually help you when, oh, sure. So if you go to Ken's assignment 2 solutions, that's a good question. So he has the formula here. So I think it's here. Yeah, it's called Sturgis Rule. So you can kind of Google it basically, right? So I'm going to put this Sturgis Rule basically. If you are kind of curious, it's a function of your, things will actually look like, it will say that your actual bins should be a function of your sample size basically. Right? So that means if your bins are too big, you start to lose the structure of your database. Because some people actually chose bins equals 8, but it wasn't really helpful because the issue is that your sample size wasn't big enough for that, right? But even if you choose a bins that are too big, please make sure you explain why you chose those bins, because even then you might lose less marks than you think you would lose if you just justify your solution. Don't just make a plot and move on, explain what you actually were doing. Okay, so I wouldn't necessarily trust a histogram when I have small sample sizes. So this is why sometimes a QQ plot looks better. So you see for this pane data here, I'm going to show you that it's actually a thing that only has 12 data points. And so you can see that, well, it actually has 24, but it has 12 subjects and 2 observations per subject. So this is a small data set. The problem with this is that you then start to ask yourself, can you even assess the shape of the distribution from the histogram? Maybe you shouldn't use that, right? So, and if this is true, is this really the appropriate test to use? Is the t-test really appropriate when you have this situation, right? And we're going to ask ourselves these questions. Your sample size is small. You already should have suspicion as to whether or not you should use a t-test, because you're given no guarantees as to the normality of the sampling distribution, which is a small sample size. So you should be a bit careful. And that means if your initial data structure is not actually normal, you really have some problems, right? So if the only way you can get away with a small sample size is if your true data generating structure process is actually truly normal. But if it's not normal and you have a small sample size, you're not given any guarantees that the t distribution is actually, the t-test is the best test to use, right? So in assignment 2, you guys actually talked about this in 1E, I think you're told to kind of give 2 reasons to why you were suspicious of the t-test, if you know whether or not you could use it. And you guys surmise that your sample size is big enough at 30-something data points to assume the central limit there might give us some kind of underlying normality of our sampling distribution. But you were given no such guarantees with a data set of 12, right? That's the issue. Okay, let's see. So let's pretend, for instance, that let's fix this typo here first. And let's pretend that the 2 groups are actually independent. I'm saying let's pretend because if you actually look at this, you would notice that it's not. Does anyone know why? We cannot assume independence by looking at this. So we cannot assume independence of the measurements between drug A and drug B. Does anyone know why we cannot from the first glance? Does anyone see what the issue is from the first glance? So the issue we have is that you're looking at a measurements of, so drug A and drug B is being measured on the same subject, right? So when you have you don't have independent group, these measurements are not independent because they're being measured on the same subjects, right? So drug A and drug B is, you're looking at measured differences from the same subject, right? So the difference between drug A and drug B in person 1, person 2, all the way to person 12. Well, obviously, there's a correlation structure when you're taking measurements on the same person. So you cannot assume independence, right? And let's see what happens when we actually assume it, when we should not, basically, right? So this function width allows you to put the pane data set, and I should put pane original, actually, right? Now, if I do this, what do I get? I get this, right? So I get this, this test, we look at the p-value here is actually 0.3077, and the t statistic is actually pretty small, right? You see that's like 1.0, right? You forget the sign, but if you put the absolute value of sign, if you put the absolute value of t, it's like 1.04, right? So that's not great. And you can see the p-value is actually pretty large because it's telling you that you don't have a difference. But there's a problem here. You see, this independence test is obscuring, the actual treatment effect itself is being obscured by the within group variability. What do I mean by that? What I mean is that you should not assume that the variance in measurements between person 1 is going to be the same as the variance between measurements in person 2 and person 3 and person 4, etc. Each person has its own correlation structure because each person is distinctly unique, basically. So when you assume independence of the samples for drug A and drug B, you actually miss the within group variability between each of the different subjects, and you actually obscure the t-test, because remember, the t-test is always a ratio between the actual difference itself and the standard error. So when your standard error is made very big because you haven't actually captured the within group variability between each subject, you get a ratio between the standard error and the difference you want to actually look at that is very small, basically. Because the standard error is getting very big because you haven't accounted for the fact that each person is different from each other. And the actual treatment effect itself, which is the difference between drug A and drug B, is too small to overcome the big within group variability. So this is why your actual t-statistic looks small and you have a very big p-value, because you haven't, the ratio between your actual within group variability, you do not account for, and the actual difference in the actual treatment effect is making the t-statistic really small, right? So let's pretend then, this is essentially why we need a matched pair design. We need to accept that we have this correlation structure and we need to account for it. So how do we do this in the R code? Well, you can see when we do the Geoq plot and we see that it's not exactly normal. So that's a good question, Ivan. The answer to that is it depends, basically. If you have a Geoq plot that doesn't look exactly normal, you can kind of use it for the most part sometimes, right? So it depends on the data itself. If you have huge outliers, you probably should do something to the outliers first. And actually this pane data set has a big outlier. So the problem is not even the normality. It's two issues, Ivan. One, the sample size. If your sample size is too small, you probably shouldn't. And then two, if you have huge outliers, you probably should do something to the outliers first, because the t-test, remember, relies on the mean itself. It's a difference of means, basically. But the mean can be very heavily influenced by extremely ridiculous outliers. So if you have a big outliers in your data set, you probably should be a bit careful to use the t-test, or if your sample size is pervasively small, basically. So you should be careful for those two scenarios. Otherwise, if you have some deviation from normality, but your sample size is big enough, you can sometimes use the t-test anyway. But probably you're going to see in this example, we shouldn't, because it has too many things that are wrong with it. First of all, there are only 12 subjects. That's one issue. And then we're going to see that we have a massive outlier that makes the mean a very poor measure of the center. So those two issues will make the t-test not ideal for this particular data set. And those are things you guys should check when you look at this. Is the reason why we might want to look at your Geoq plot or whatnot before you start doing the t-test. if you want to put like extra logical steps in your assignment, even if you're not asked to do these things, you might want to check and see for yourself. So the grader sees you going the extra mile base. That actually what constitutes a 10 out of 10. Like a 10 is like when you do something extra that you weren't asked to do to kind of contextualize your solutions, basically. Like for instance, if you're not asked to do a Geoq plot, but you looked anyways before doing the t-test, that's like extra basically. Okay, so I put paired equals true because the default is false. The default is to just assume independence. So when you put paired equals true, you're then saying your test is not independent. If you remove this paired equals true, it becomes like paired equals false, which is the original t-test you saw, right? So now what happens when we actually run this, you can see that your p-value is actually smaller because now we have accommodated this within group difference. And by within group, I mean that each person has its own variability that's distinct from each other, and we've accounted for this space. Now the ratio between the standard error and the difference in the treatment effect is now larger, as in the ratio is actually bigger because now the between the group effect, the treatment effect is more salient when you control for the standard error, basically. Now, if we choose, so you can see that whether or not you reject null hypothesis, it depends on the alpha you choose. Here's another fast fact, right? So when you say something like fail to reject null hypothesis, this is going to be true if you choose your alpha to be 0.05. So specify this. You can say that under alpha equals 0.05, we will actually fail to reject null hypothesis. We will not be able to conclude that there's a meaningful difference between pain mitigation between drug A and drug B. Right? But if you choose your alpha to be 0.1, suddenly there is a significant effect. You will reject null hypothesis if you choose that alpha base. So it depends. You can choose your own alpha. Whatever alpha you specify, make sure your conclusion makes sense within the framework of that alpha. But you can actually see that because independent t-test was really not correct, there is almost no alpha you choose that will cause a rejection of the null hypothesis here. It's just so, your within group effect is so big, it completely obscures the treatment effect. So there's nothing can do with any alpha level to reject null hypothesis here. Okay, so now the issue is that I'm telling you guys your sample size is kind of small because you can see the degrees of freedom is like 11. And now you should ask yourself, is this the only problem? Like what else, right? Is there any other issues we have with our data? And to this, I'm going to actually show you guys the Geoq plot. Right, so this is a note here. I'm assuming so far that things are normal. Now let's see if we're onto something. Is it really true that we have normality? Okay, so I'm going to introduce a new column. It's called pain diff. Now, if drug A is actually normal, distributed normally, if the actual response for drug A is normal and the response for drug B is normal, the difference itself should be normal. So the pain difference should be distributed normally if this is making sense. All right, so now let's see what we get. And actually, now that I have this pain difference here, so I call it pain to make it different from pain original. It's now called pain. And so I've actually mutated, allows me to actually add a new variable. So under mutated, it added a pain difference basically. All right, so now let's see what happens if I run this. So there's a reason why I didn't choose a histogram. If I choose histogram, so you can see that not all demonstrations make sense, right? So what if I, for instance, put histogram? What happens? You get something that looks ridiculous. So sometimes not all displays make equal sense. Notice that because you only have 12 observations, you really get nothing about the shape of the distribution from looking at this histogram. Because there's only going to be 12 data points because you only have 12 different subjects. So when you take the difference along those subjects, you get 12 differences basically, right? So you get nothing. Your empty bins in here basically. You get, no matter how small you make your bins, and I made it small by making it 6, you still get no underlying structure. So the histogram is probably not your best bet here. This is why I use box plot, because you have to think about your answer sometimes, right? So it doesn't make sense to use histogram because there's too many empty bins basically. If I use box plot, I get this thing here, which shows a huge outlier down here. Now this is the issue. Now the t-test again is relying on the mean, but have a look and see that we have this huge outlier that's going to pull the mean downwards. And what's the ramifications of this? The ramifications that it's going to look as if the mean difference in pain is far from 0. Now, if drug A and drug B has the same treatment effect, right? If the effect is actually the same, the difference in pain scores should be 0 between the two different groups, right? It should be 0 if there's really no difference in the two treatments, basically. When you have this big outlier, the poles are far from 0, what is it actually saying? It's saying that because our pain difference is actually drug A minus drug B, it's saying the drug B is actually better than drug A because the difference is actually 0. So the pain, or it depends. I think this is actually pain score, which actually means that it's actually probably saying the drug A is better than drug B because the pain score is higher in drug B. So that means people did better in drug A, right? So what it's actually saying is that probably potentially the pain score is actually higher in drug B. So drug A probably did better. Right? So now the issue with this is that that's only based on this one huge outlier that pulls the whole mean backwards. Perhaps if you remove this outlier, there's no real difference in the actual pain score between different drug therapies. So when you have a t-test that relies on the mean, and the mean is itself corrupted by these outliers, you should be suspicious, basically. And this is why we look at this graphical display to see what we're dealing with. And you can actually see it even more saliently if you look at the QQ plot, right? Because notice that things trend the line, except this point down here that looks really off the grid. Right? So telling us maybe you probably shouldn't use the t-test. So this is to answer your question. We don't want to use the t-test here because of this big outlier. It doesn't help us, right? Because even if the other points look okay, once you remove this point, you may be able to use a t-test, perhaps, but you probably shouldn't use it with this point inside your data set, basically. Okay, so now let's not use a test then that relies on the mean as a measure of center. So if you cannot use the mean, your next bet is to use the median, basically, right? So let's switch gears then and go back to Professor Butler's SMMR tool, right? So the Sahihi weighted median test. So you might ask, why are you doing pain difference from 0, basically, right? So I'm trying to track whether or not the difference between A and B is bigger than 0, because if the difference is bigger than 0, or even if it's less than 0, it would mean that one drug did better than the other in terms of pain management. All right, but if the difference is exactly 0, so the null hypothesis is actually the following. So this is, just to formalize, this is the null. What I'm saying is that, it's, mu of like A minus mu of B. And notice it's always the population level is equal to 0. And the alternative is like, mu of, A minus mu of B. Sorry, in LaTeX, the actual thing is like not equal to 0. This is actual like command, right? So it's not equal to 0. So this is a two-sided task. What I'm saying is that the difference can be negative or positive, but I'm looking to see if it's different from 0, basically. Now, instead of actually looking at the mean, it's going to look at the median, because obviously, what is it going to do? You guys know from the previous lectures that what it does is it actually checks to see how many of the actual pain differences. So if you look at it's going to look at these differences here, right? So pain. It's going to look to see how many of these differences are actually above or below 0, basically. Right? So it's going to look at these and say, okay, is it above or below 0? How many of them, and how bad is the difference? How bad is it from 0, basically? So it orders it up, right? So because our median is 0, it's going to look to see. And the question is then, is it true that, so again, let's have a quick look. Is it true that the proportion of pain differences that are above 0 is radically different from the proportion of pain differences that are below 0? If it's about 50% for each one, you didn't get any significant effect. You need to see a lopsided difference to determine whether or not it's a true difference, right? If you have a 50% or above 0, 50% or below, you didn't get a true treatment effect. All right, so this is the sign test. We're doing a two-sided test here. By the way, I've specified the test, which means that what you actually have is this here. Now, notice the p-value is actually even larger than the p-value you had before. So when we adjusted for the paired t-test, notice that we have this test here. Does anyone know what's interesting about this? Like, why is this, anyone see why we actually have a larger p-value with the median test? What happened with the p-value for that? What happened with the t-test? So the t-test actually had the big outlier that when it was added to the actual mean difference, right? So when it is added, so the test is actually this. You might recall the test is over here. So when you look at the actual sample difference, so you know that when we're performing this test at the population level, but to actually estimate this thing here, we're going to use the following. We're going to use, X, we're going to use the mean of, like, let's say, group A minus group B. Sorry, I'm going to do this, by the way. Right, so this is actually, we're going to look at the sample mean, basically, sample mean of this, right? And the thing is that the question is, how far is it from 0? If you add a very largely negative sample to the mean, it's going to actually pull the sample mean down. And it's going to make it seem like it's in this scenario here, when it may actually not be, right? So when you adjust it for the median instead of the mean, it suddenly recognizes that you actually don't have an effect, and it makes a p-value larger than what it appeared to be. Right? So you can see that the actual p-value was actually made smaller than it should have been by the huge outlier you saw. So this is why sometimes when you have those big outliers, you may not want to use the t-test. Any questions about this? Okay, cool. So the last thing, I guess, is the moods test. So the moods test is actually the built-in function that Ken has, and it's actually similar to the sign test. But the distinction here is that with the sign test, you guys give a particular median that you want to test. So I fed the median of like 0. But the moods test actually looks at the overall grand mean of all your data. So instead of you specifying a mean, it actually orders up all your data and then looks at the median and then says how many observations are above or below a median, basically, right? So this means that it's a bit of a different test, right? It's using a different, so the sign test use the binomial distribution. The moods test is using a different distribution basically. It's not using the binomial, right? So remember, the binomial distribution is like yes or no, it's above or below the median. This one is not using the binomial test. It's using the chi-square test. You might say, why is that the case? Well, first of all, when you ask how many observations are above or below your particular median, what are you actually doing? Well, you're actually, first of all, it's a binomial thing in the sense that, like, are you above or below a particular median? Yes or no? That is binomial, but we know that when we look at a very large n, things that are binomial start to look actually normal, right? So if you look at the actual sampling distribution for a binomial thing, when you subtract a binomial parameter from its own mean and you standardize it, right? So you have this thing that looks like the following. You could have something like, z is equal to, x minus, np, which is a binomial thing, right? Divided by, you guys know it's like np1 minus p, right? This is actually, it's normal, right? This is an interesting thing. You guys kind of know this is central limit theorem. It tells you this. So, right, this is the central limit theorem. You can see that it looks normal, right? And actually I should put square root of this, right? Right, so this is normal for large sample sizes. So when your n is large enough, right, you get this thing that looks like a normal. But when you square a normal, you get something that's actually chi, basically. So the moods test is actually a chi-squared test, right? So you know that, also, just make for a note here, also, it's the case that z squared is, distributed chi. This is me also teaching you guys LaTeX if any of you are kind of curious, right? Right, so you get a chi. Right, so when you square this normal, you get a chi. So this means that the moods test is actually looking at a table of things, and it's either the case it's above or below the median, and it's actually going to be a chi. The test is on a chi-square distribution. So let's look at another example Ken had, which is daylight savings. So the question is like whether or not people believe that you should end daylight savings, right? So do you agree that daylight savings kind of sucks? That's, here's a table of females and males. So it's a table of 40 by 2. You have 20 female responses and 20 male responses, right? So if I look at the tail of like, you know, DST, you see the males basically, right? So this is a table of all the 40 responses, 20 for each gender. And then I'm going to find the grand median and then do the chi-square test as per the moods test, right? Because it's we know that central limit theorem tells us that things are binomial. If you sample large enough, if you keep taking different samples of size n, right, and where n is large enough, you can construct a sampling distribution on this proportion, right? That looks obviously normal. So you keep literally taking samples of size n, and you keep estimating new values of p. This creates a distribution that looks normal. And when you take a square of that normal, it's chi. Okay, so let's look at the median of this thing. Oops, that's not right. I meant to do this. DST, right? And I went to do agree. Oh, let's not look at this. So first I'm gonna make you a table basically. This is a table, right? This is a table where I'm not actually going to, I haven't actually considered median just yet. This is a table of just how many people from each gender said yes or no. So this is actually what we call a contingency table, right? So in the contingency table, you actually can see that females who said no, they don't think that daylight savings should be changed or whatever, is probably like 11. Yes said 9. Males, 3 and 17. I think that actually might be how many of them agree with daylight savings. We could check Ken's notes. So let's actually have a look just to be clear. Let's see. I want to make sure that the context is making sense. Oh, by the way, he's going to teach you guys ANOVA this week. Okay, let's see. Daylight savings. Oh yeah. So suppose you want to know whether or not we are in favor of having daylight savings, right? So this means that females said yes, 9 of them, and then 11 said no. And the males, ironically, 17 said yes, they agree with daylight savings, and 3 said no. So this is actually the table we constructed for this. And now I can do a chi-square test. And the question is there a difference in genders who said yes or no to the actual difference in daylight savings, right? So if I run this test, I get this p-value, right? So it looks like there's a significant difference, right? In the sense that like men are more likely than women to agree that to say daylight savings. But this test is actually being performed on the mean, right? So you can see that I haven't adjusted for that. I haven't actually looked at the median itself. I'm looking at the mean itself. Right, so to do the moods test, I should actually be looking at the median itself, like how many observations are above the median, how many are below. Whereas this one here, I just literally actually did the test around the mean. As you can see from here, it's around the mean because n times p is actually the mean for the binomial distribution. So if I look at the median instead, right, and this is what I'm doing here, I'm looking at this. So first of all, you can see that this is actually yes, yes, no. This is actually not even, I can't use this just yet. So I translated this variable basically. And what I did was I created a new variable, right? And I think I have it here. It's called DST, right? So it's called DST. Mutate if else. So I called it agreed 1. I lost it in my code, but I called agreed 1 equal to if else. So if, for instance, the agreed is equal to yes, give it a value of 1, otherwise 0. Right? This is me creating a new variable called agreed 1. So because I cannot use these values as 1, 0. I cannot use yes, yes, yes. I have to create it to like, I need to translate it. So I did. Oh no, what happened? Oh, it's because I need to attach. Oh, because of this, yeah. Yeah, there you go. So if I look at this, now it does the following. You can see that it changed this to agreed 1 because you cannot compute the mean on categorical things. You need numerical values to compute the median. So I translated these to actually numerical values. And then I found the median. So you can see that M is actually 1. The median appears to be 1. So now if I do a new table along the median, so how many of them are above the median, how many are below, I get this, which kind of looks a lot like the original table basically, right? So it looks like here, the table's the same, but it's not always the case. So in this case here, the median and the mean kind of have similar like is the exact same because I'm working with like a distribution where it's binomial, like as in the outcomes are yes or no, but it's because it's, sorry, not because it's binomial, because of the fact that like my actual outcome is either 0 or 1. It turns out the median is the same as the mean in this context. But you can have pervasive things happening where your actual median and your mean don't look the same. And then the table shifts itself according to where your median happens to be. Just so it turns out here, because the answer is either 0 or 1, then the median and the mean kind of look similar, right? But it doesn't always have to be the case when you don't have a yes or no outcome. So if I look at the median of this, which is actually a built-in function in Ken's thing. So I gave the data frame, the variable, the numerical variable itself, and the groups. This is the group difference here. So I wanted to look at the difference on gender. I got the following, which shows me a p-value of like almost 1, which is going along with the line of like the very small p-value you saw over here, right? Which is saying that like obviously men are more likely to agree with the idea of like daylight savings, right? So this is a very silly example, obviously, because you can see that because I only had 1 or 0 as answers, it kind of made the median and the mean look the same. But in his lecture notes, he has a different example with the kids data set, where you actually, the p-value for the mood test is not the same as the chi-square test. And you can see where you're kind of looking at those kind of things. So where you might want to use something different. When you don't want to use the mean, you might want to use the median instead, and you would use the mood test. Yeah, that's it for now, I suppose. So I'll post this on my YouTube channel. Oh, if you guys are curious where the example is, you can see that he goes through an example called kids. So this is where he does a chi-square test, and you can see that it's going to give you a different thing. It'll give you a different p-value than if you go through, I think you might go through the example with just the t-test, and it gives you something different, but I haven't looked through the lecture notes quite carefully yet, so have a look and see. But anyways, I guess I'll see you guys next week. And good luck.